Thank you very much for the introduction, and thank you all for being here for the presentation of our project ROPfuscator Robust Obfuscation with Return-Oriented Programming. This is a joint work with Fukutomo Nakanishi, Daniele Ferla, and Lorenzo Cavallaro. But before delving in the details of the project itself, I want to give a brief overview of what obfuscation is. According to the formal definition of the verb to obfuscate, it's the act of making something less intelligible and harder to understand, especially intentionally. In computer science, this can be seen as a set of techniques that are like smoke and mirrors in the eyes of analysts. And obfuscation can be done at source level or at binary level. And among the most common commercial and non-commercial obfuscators, we have Tigress, VM Protect, Loki, Obfuscator. And the use cases range from the digital rights management, software licensing, intellectual property protection, and anti-tampering. Now, among the most common obfuscation techniques, we have dead code insertion, that is the insertion of single instructions or code snippets that have nothing to do with the actual calculations. Control flow flattening, that is the act of transforming a single function into a loop that is broken into multiple basic blocks out of order that are used through a switch case statement. Code transposition, that is the act of reordering instructions such that their side effects have no implications between each other. Then virtualizations, that at least in obfuscation, is the act of moving the host binary into a custom bytecode for a custom instruction set. And then mixed Boolean arithmetics, that is the act of transforming simple operations into expressions that are heavily based on Boolean and algebraic properties. Now, let's jump into ROPfuscator. ROPfuscator, as the name might imply, uses return-oriented programming. But what is that? Return-oriented programming is an offensive binary exploitation technique that is used when code injection is not possible due to stack protections. And the building block of return-oriented programming is the so-called concept of gadget. That is a series of instructions always terminated by a return instruction. Specifically for ROPfuscator, we use micro gadgets that are single instructions that are then appended by a return instruction. Then the composition of these gadgets is called a ROP chain and allow arbitrary code execution. But let's take a look at the anatomy of a ROP chain. So let's consider a function that is vulnerable to a buffer overrun. So we have our buffer that gets overrun, and then we can control the return address. But in this case, we cannot actually just jump to the code that we injected. We have to reuse the code of the program itself. So by concatenating different locations in the program itself, then through the gadgets, we can come up with an arbitrary algorithm. And so why ROP? As I said earlier, ROP is an offensive technique, and we asked ourselves, can we actually repurpose this for defensive measures? As since return-oriented programming is unnatural in CFG disruption. So we present ROPfuscator, that is a framework based on LLVM to obfuscate LLVM-based languages that is open source and that you can find on GitHub now. So let me give you an overview of the pipeline of ROPfuscator. First of all, we start from the source code that is fed into CLang, and that CLang then is going to generate its internal bitcode representation. Then the bitcode is fed internally to the low-level compiler that is going to generate the host assembly. In our case, x86. Then this is where ROPfuscator comes into play. ROPfuscator is split in 3 different phases, where the first one is the ROP transformation. That is a one-to-one mapping between an instruction or multiple instruction and a chain. In this case, in this step, we need a library to extract the gadgets from. Then we inject opaque predicates, and finally we perform instruction hiding. We're going to see in a moment what these things are. Then once the obfuscated assembly is generated, it's passed to the assembler linker that links everything together and generates the final executable that is ready to be shipped. So I left out intentionally another very famous and common obfuscation technique, that is the opaque predicates. Opaque predicates are conditional statements that are actually always evaluating to the same value. So again, it's a complex, it seems to be a complex condition that actually is always going to do the same thing. And usually the calculations are NP-hard problems to ensure the intractability of their simplification. Finally, we have instruction hiding. It is a technique that we introduced that can be seen as a composition of dead code insertion and code transposition. So in this case, we take some instruction from the opaque predicates themselves and we rearrange them while also adding dummy instructions to make the analysis harder. So let's jump to the results. We evaluated ROPfuscator on 4 different scenarios of increasing difficulty. The first 2 are static analysis, where the first one is the simplest scenario, that is a generic static analysis. Then we take in account a static analysis that is ROP aware, and then we jump in the dynamic analysis, where for thread C, we have state-of-the-art symbolic execution, and for thread D is dynamic analysis that takes in account that return-oriented programming is being used. So we answer to 5 questions. Completeness, so what is the code coverage of ROPfuscator? How many instructions from the full binary can we actually transform into ROP chains? Then performance, which is kind of self-explanatory. What is the overhead that ROPfuscator introduces? Correctness, and as a compiler, we must make sure that the semantics of the program are not changed from the compilation process. And robustness. So how robust is ROPfuscator in protecting the binary from external analysis? And practicality. Can we actually use it on real-world scenarios or programs? In the next slides, you're going to see 5 different configurations that we used. The baseline, that is the not obfuscated binary. ROP only, that is the first phase only applied. And then ROP plus opaque basic, opaque predicates that are basic. What are these things? They are opaque predicates that are actually calculating very simple operations that are intended to throw away beginner reverse engineers. So nothing really robust. And then we actually implemented opaque predicates that are able to withstand automated analysis. And finally, the last configuration is the conglomerate of all together. So we tested the ROPfuscator on the GNU binutils, spec CPU 2016, and the VLC media player. For completeness, on average, ROPfuscator is able to obfuscate from 60 to 80% of the instructions. And ROPfuscator is heavily influenced by compiler optimizations. Whenever the optimizations are not present, the coverage goes up. This is due to the proof of concept nature of the implementation. And at the same time, the library version influence the coverage as well. Then for correctness, we made sure through spec CPU that the output of the baseline program and the obfuscated bar programs are the same. And then for performance, in this table, you can see that the ratio of spatial and time overhead. In the central column, you're going to see the baseline used as a reference, and on the rightmost column, the ROP transformation phase only used as the reference. So time-wise, we have an overhead that spans from 10 times to 100, 200 times slower. And then size-wise, from 10 times to 1,000 times bigger. Finally, for robustness, we can see that by adding these layers of obfuscation on top of the ROPification, the robustness increases. And just to give a small insight, opaque predicates are needed to withstand analysis of the return addresses of the ROP chains, because otherwise it will be trivial to just jump to the address of the gadgets. So by adding all the obfuscation layers together, we are able to withstand also automated analysis. And finally, for practicality, we wanted to use a real-world scenario. And for this experiment, we played a 30-second movie clip from a commercial DVD with VLC media player. But in this case, we also introduced another configuration that is the balance configuration. In this case, while the other configurations are obfuscating the entire binary, the balance is not, and it's only targeting selected functions. In our case, we decided to target the key derivation so the cryptographic functions from libdvd CSS to make sure that the actual routine that decrypted the movie was protected. And in that case, we can see that with ROP only is the only configuration that makes VLC usable, but the others, while being way more robust, are making the program basically unusable to run. While using with the balanced configuration, we are able to achieve robustness and performance. So the takeaway is that ROPfuscator introduces significant overhead, but we, by selecting the functions, we can achieve a nice compromise between robustness and performance. Now, between the paper that we presented and is being published, we made already some changes, and we changed the build process, and we are ensuring reproducibility of the build process itself, and ROPfuscator compiling whatever. And this is done with Nix. That is a declarative and functional package manager and language. And we also removed the dependency from the system's libc library. As a future directions, one of the first steps to do is to move away from micro gadgets to more complex chains of gadgets that also should allow for better performance and an extended architecture support, moving away from x86. So in conclusion, we presented ROPfuscator with a unified threat model, and we experimented on code coverage, overhead, correctness, robustness, and practicality challenges. ROPfuscator is available open source, and we're gonna wait for you at the demo session. And we would like also to obfuscate arbitrary packages from the Nix repository. So come visit us, and thank you for your attention.
Any questions?
Thank you, great talk. I was wondering, so you had that slide, I think 18 or something, where you say, okay, if we add the hiding, it defeats the dynamic ROP analysis. So can you maybe give some insight as to why? And also, I was wondering, okay, if you had the instruction hiding just by itself, would that also defeat the other analyses that you have, or not?
No. So instruction hiding is another layer of obfuscation that we added because opaque predicates alone weren't enough. Because usually there are the obfuscation algorithms that know what opaque predicates are, what code transposition is, and so on. So instruction hiding can be seen as an arbitrary layer of obfuscation that can be used to protect the ROP chains. Same thing actually as the opaque predicates. In fact, one of the ideas for the next steps is to just change opaque predicates instruction hiding for an arbitrary additional obfuscation layer. So they could be like